Everyone, this is my first video, and in this video I will show you how to perform a buckle analysis, linear buckle analysis on a simple model using Abaqus finite element solver. Okay, here you can see all the model that I prepared for this tutorial, and now step by step I will show you how to do each step. Okay. When you start to model something, you have to first of all build your model or import your model. You can import any type of model, for example using particular programs like SolidWorks or CATIA, and you can use the command in file, import, and you can import the sketch, a part, an assembly, or the model. In particular, you always use model because you will import a 3D or 2D model from CATIA or SolidWorks. In this case, because the model is very simple, is a cylinder, as you can see, a simple cylinder, I use the Abaqus CAD present in the program. With a double click you can create your part, naming the part, selecting the modeling space, planar, axis symmetrics, or 3D. For the big for a big part of models you will use always 3D, because you will work in the 3D space, and working in 3D means that the model will live in a 3D dimension, and this don't mean that you cannot model only in plane stress or displacement model. You will be allowed to model anything in 3D space. There are mainly 4 types of part: deformable, discrete rigid, analytical rigid, and Eulerian. The one that we will use today is deformable. You can select different shapes: solid, shell, wire, and point, and for each one of these shapes you will be allowed to use a different element. For solid, the solid element; for shell, shell element; for wire and point, obviously you will use only one-dimensional elements. In this case I selected shell, and then you can model your model, sorry for double word: planar, extrusion, revolution, and sweep. For example, in this case I use extrusion. What's mean extrusion? If I double click here, sorry, okay, I can sketch anything in this part of the program, drawing lines, point, or anything you will need, like this. You can also delete some of these, and anyway I drawn this circle. This circle has a radius of 0.25 meters, and with this tool you regulate and fix the dimension of your geometry. In this case, this circle will be always of 0.25 meters of radius. When you have sketched your model, you can click on done, and then the program asks to you how will be the depth of your extrusion. In this case, as you can see, the modeler starts from the line that I drawn in the sketch, and extrude a shell geometry from that sketch, and the depth is assigned here. In this case I assigned 0.5 meters. Okay, in this case the model is already done and is ready for the next step. In the part you can assign sets, surface, skins, stringers, and other many type of any other type of characteristics. In this case, for this simple model, we have to assign a section. In older Abaqus version, you have before to define materials and section, profile. In the modern, in this version 6.12.1, but also in 6.9, 6.10, you can define the part that you need step by step. For example, I need to assign a section. I select the geometry that I want to model, and clicking down, I can, by pushing here this create section, I can create a new section, for example. In the create section tool you can decide which category of the section you need: solid, shell, beam, fluid if you are doing a GFD simulation, or other. In this case we have to select shell because the geometry is a shell geometry. There are mainly 5 types of different sections: homogeneous, the one that we will use; composite for composite material; membrane if you are going to use membrane element; surface; and general shell stiffness. In this case you introduce an ABD matrix that model the materials, and this is very useful when you model composite but you don't want to use classical lamination theory. So when you want to introduce your own ABD matrix, in this case we select homogeneous, and then you have to put some values. The shell thickness, in this case we use a constant value, for example 2 mm, and then you have to select the materials. If you haven't defined the materials, you can push here and define immediately the material. I'll do this in the next step. Then select the integration point. By default Abaqus select 5. This is a good point where to start. And then the thickness integration rule. Simpson is always good for general purpose. There are also advanced properties, but in this case we will not use this. Click OK, and then you have to decide the shell offset, or well, you are assigning a thickness to your model. So the program will compute this thickness from a line, and this line and the thickness will be laid on top surface, bottom surface, specific value. You introduce the offset ratio, or middle surface. I use always middle surface. This mean, and click OK. This means that if your thickness is 2, 1 millimeter will go up and 1 down from the geometry that is present here. If you select up, the shell will start from the exterior surface, and in the other sense, if you select down, it will start from internal surface. In this case you can see that model become yellow because there is a problem with the section assignment. There are 2 different sections. In this case I delete or suppress is the one in excess, and the model became green. When the model is green, it means that the section given is okay, it's right. Then we can mesh the model. You can decide to mesh the assembly or the part. I prefer always to mesh the part, because I mesh each part step by step. You can mesh using global seeds that give a global seeds to all the model, and in this case is the best way to mesh your model, this model, because it's very simple. In other model where the model is more complicated, probably the global seeds is not really accurate. This value say the approximate global size. In this case is 0.025 meters. And this value is the size of each element. In this case we are using square elements, so all the elements has the same length. By pushing here we can mesh, and we can also decide different mesh control. Free in this case, or sweep. Free will generate randomic mesh, and this type of mesh is not very accurate in this case. In this case the best way is using a sweep mesh. Sweep means that you start from a point, in this case, and start to mesh step by step, following the perimeter of this cylinder. And as you can see, the results is very nice because the mesh is very homogeneous. Once the mesh is done, you can continue to create your model. Now we look to the material that I created before. I introduced the density of the materials in kilogram on meters, cubic meters, and then the elastic properties, the Young modulus and the Poisson ratio. In this case I want to model anisotropic materials without plasticity, because it's a simple linear buckle analysis. Then you create the assembly by clicking here and selecting which part you want to introduce in your assembly. In this case we have just a part, so it's just the cylinder itself. By this point you can assign different features like the datum Cs, and also reference point for other purposes. There are also the sets. The sets are an inclusion of different or similar nodes. For example, I selected two groups of nodes, down nodes and upper nodes. Down nodes are here, you can see, and up nodes are here. And why I selected these nodes? Because I will assign different boundary conditions to these two groups of nodes to perform the buckling analysis. To select sets is really simple. You click on set, decide the name, set A. You can select which type of set you need. For example, you can select a geometry, node, or element. In this case I select nodes. Click on continue. You can select individually, one by one, clicking on shift, but it's very time consuming activity. By angle, but in this case it will select all the nodes of your model, or by feature edge. In this case, the feature edge corresponds to the line that go on the circle, and it's very nice because you can select all the nodes on the edge. Click done, and the set is done. I recommend to you all to check always the sets and the surface if you select surfaces or you want to use surfaces when you change the mesh, because if you define sets using or surface using geometry during the analysis, these sets and surfaces will not change, because if you change the mesh, the geometry will not change. But if you select element or nodes, they will change, and so you will need to reselect your nodes or elements. I show you. If I decide to increase my mesh, I click here, and this message means that I'm going to mesh the assembly, but I meshed each part independently, so I have to click here, part, and then I can do all what I want. For example, I can write this, I apply, delete mesh. Okay. Now the model is yellow, not for error, but because the program has different color for each mesh controller. Red is for free mesh, yellow for sweep, and green for structured mesh. I can remesh, yes, and okay. 540 elements and being generated on part 1. The mesh is finer, as you can see. And now look what happened. If I double click on instance, you can see this signal means that he doesn't recognize the sets that I done. I delete this one because it's useless. And now I have to reselect the nodes. Okay, done. It's pretty easy, but you have to do this always when you change the mesh. If you forgot to do this, probably the analysis will be aborted. Instead, surfaces are selected using the geometry, and as you can see, they remain defined. Okay, so the last part is to set the type of analysis. In this case, I created a buckle analysis. To create this, you just click on steps and then decide general analysis or linear perturbation. In this case, I select linear perturbation buckle and I named it buckle, this one. Obviously, you have to click on continue. By this point, you can have the description. In this case, there is no the no linear geometry is off. You can select the eigensolver. In this case, I use subspace that is common for this tutorial and good for this tutorial. I can ask to Abaqus to extract any type of eigenvalues. In this case, I request 5 eigenvalues, and the default value will appear here, but you can increase. I always use the vector per iteration that Abaqus suggests to me, but sometimes I see that I have to increase the maximum number of iterations that Abaqus perform until he found the solution. This is useful because sometimes some models are not really simple, so the solver may have no success with the default 30 iteration. So in sometime I increase by one order the number of iteration. In this case 30 is okay, but I leave 300. And okay, for field output and history output, do the simple analysis that we want to perform, a linear buckle analysis, we can use the default preselected field. And then we have to set load and boundary condition. Before this, I want to introduce some constraint, and I want to introduce this constraint because why we are simulating this? Because we have a cylinder made by aluminum and we want to study the linear buckling value, so the critical load, by which this structure will be unstable. And also we are interested in the modes. What we are simulating? We want that the down part is fixed or well encased, and by this other one will be constrained in all degree of freedom except the translation on zeta axis, where the load is applied. So there are many ways to do this. I prefer this one, creating constraint. So you have a set of nodes that are slave nodes and a master node here in the reference point, and I want to make this node slave to this one, and I did this using rigid body definition. By constraint, rigid body. There are also other ways using MPC constraint, not tie, but or rigid body or MPC constraint. You can also use a equation. In this case I used rigid body. You can select the region, and can be an element, a node, different type of node, tie or pin, or analytical surface. In this case I select pin nodes, and then you have to select this region. You can select sets, for example down nodes, if I want to select these nodes, and then the reference point, just clicking here, and okay, it's ready. And you can do the same for the other, for the upper side. Oh, before I forgot, to introduce a reference point is really simple. You double click on constraint, and this menu, that is the interaction menu, you can navigate in the model using also this nice menu, interaction, reference point. Click here and you can select the point. For example, due the geometry, there are many points present. You can, for example, select 0, 0, 0. It is this point, and then click OK. Sorry, the interruption. So the reference point is done. You can find the reference point in assembly here, and the reference point 1, 2, and the 3 that I created. I delete this one because it's useless. Okay, so using the interaction and the constraint, you can select constraint 1 that constrain the down nodes to reference point 1 by using pin nodes, selecting down nodes, and then point, picking the reference point 1, and okay. The same for upper nodes. Now it's the time to assign the boundary condition. Boundary condition 1 is assigned directly to the reference point 1. Stress perturbation and buckling mode calculation, all 0, because we want that these nodes will be not only fixed by translation but also for rotation. And the second one, the same, but the translation on zeta axis is free, because we want that only this displacement will be available. And then applying always the load to the reference point 2, we set 0 for x, y, and zeta, the third component of this vector. I select minus because the direction is minus, and 1 because the value, the eigenvalue, will be proportional to this value. If you set, for example, another value, you have to multiply your load for the eigenvalues to have the critical load. In this case, if I use 1, the first eigenvalue will be the linear buckle load. So my advice is to use always 1, because it's simple. You have not to multiply this to your results. Oh, how to assign a load? Click on load. You have many different type of load. You can also have thermal load, acoustic load, fluid, electromagnetic, mass diffusion, or other. In this case, we use concentrated force. You can select the step. Obviously, in the initial part, you can not assign load. Buckle, continue. You have to select which part of your model will be load. You can assign load also on geometry, but the best way is to assign the load on nodes on sets. In this case, we know that all these nodes are constrained and are slave of this central reference point. So if we assign the load to RP1, we will assign a load to all these nodes. And by this, why I did the sets and the rigid body constraint. By clicking done, you can select the reference system. In this case, I keep global because it's okay. This 0 because this direction, the first direction, the load in this direction is 0, 0 in the second, and minus 1 because we want to compress this structure. And done. And the second, and the load is created. You can see the little vector here. Now I delete this one because it's useless. And finally, we can save your model, and you can create your jobs, naming example buckle load. You have in this case is a full analysis, and you can also parallelize your model, but due this is a linear analysis, you cannot use these two tools. So just click OK. Or you can also add a subroutine, but in this case we don't use a subroutine. And OK, we are ready to do the analysis. Before this, I show you a trick, because always the eigenvalue extraction and the buckle analysis are used to introduce in your in another model some imperfection given by eigenmodes of your linear buckle analysis, and these are very useful when you want to study the stability of your structure. And to do this, you have to extract the displacement, or the eigenmodes from your model, and to introduce this using keywords in another model. To save your results into a file named as the jobs, for example, in this case, the file that contains the results will be buckle load.fill or file. And you have to add here this line, node 5 u. This keyword will allow you, or allow to the program to save all the results in a little file, and you will be able to use this file to perform other type of analysis that I will show in the future tutorial video. Okay, and now submit. In some case, if the model is a bit difficult or have many parts, it's always better to do a data check. Abaqus is a very nice program and very user friendly, because give back to you a lot of information if the analysis doesn't work or abort. And now the analysis is completed. These are the results of the analysis. Under format geometry, the loads by this direction. This is the first mode, as you can see, and this is the load that caused the collapse of your structure, and this is 1.05 E6 Newton. Obviously, if you increase the load, if you go up in the eigenmodes, the load will increase and the modes will change. The second, the third, the fourth, and the fifth mode. Okay, the tutorial is end here, and I recommend to you to subscribe my channel, obviously, and also to give back some using comments or mailing me any advice for the channel. If you have particular issues, problem that you cannot solve, or if you want to share something that you know that is useful for all the community, just type a comment or mail me. I hope you will enjoy this video and my future video.